Okay, now the question is, what's the distance between v and w, the v vector and the w vector? Now, we just calculated it. It is 2 times the square root of 2. We know that. We know that by the Pythagorean theorem. But can we do that in terms of the definition of length? So, how would you express the distance between v and w as the length of a vector? What vector would it be the length of? You should stop and think that through before you see me answer it, but I'm going to go ahead now, and I hope you did. Well, we know that this vector is w minus v, right? And the length of this vector is how far apart these points are. So it's magnitude of the vector w minus v. And what is the magnitude of w minus v? How are you going to write that down in terms of the definition? Write the blame thing down. It only takes 5 seconds. And if you don't understand, think about it until you're either sure you aren't going to get it or until you're sure you've tried everything that you can. Okay, that's very important. Okay, so what you write down is, well, the length of a vector is the square root of its dot product with itself. So it's going to be the square root of w minus v dot w minus v. That's it. Okay? Well, now, how are you going to apply that? W minus v is, here's your v and here's your w. What is the w minus v vector, and what's its dot product with itself? Write it out. And hopefully you have. So this is what? Well, w minus v, well, that's 4i minus 2i, which is 2i. And negative 5j minus 3j is minus 2j. And we dot that with 2i minus 2j. And we get what? Using the row column thing again, it's 2, negative 2 row vector and 2, negative 2 column vector. And this equals the square root of, well, 2 times 2 is 4, and negative 2 times negative 2 is 4. So I'll say square root of 4 plus 4, which is the square root of 8, which is what we got here. And of course, that's equal to 2 square root of 2, and it's important to do that simplification. Anytime you have a square root, you factor out all squares. Okay? There. So we have it, and this agrees with the Pythagorean theorem. Okay? Now, what's the distance between, let's say, the vector 3i minus 5j plus 7k, and let's call this v, call this w, any numbers will do, negative 4i plus 6j minus 5k. Okay, what's the distance between these vectors? Now, it's going to take a minute to write this out, so I hope you have, because I'm going on. Okay, well, distance is magnitude of w minus v equals the square root of w minus v dot w minus v. Now, w and v aren't the same as they were up here. We have new vectors. And the thing that's different about this, and it's not a big difference, it's an easy difference to deal with, it's going to be square root of what? Well, what's your w minus v vector? It's negative 4i minus 3i, which is negative 7i, 6i minus negative 5j, 6j minus negative 5j, which is 11j, negative 5k minus 7k minus 12k. Probably going to regret using bigger numbers, but they should be easy to deal with. And then it's dotted with itself. Now, I hope you worked that out before I wrote it down. But that's what it is. That's all it is. You just do w minus v, and there you have it. Well, what's this equal? Now, I could write out the row vector. I guess I will. But this is such an easy calculation that pretty soon I'm going to start out. I'm just going to go through by writing the result down. Okay, but we have negative 7 times negative 7, which is 49. 11 times 11, which is 121. And 12 times 12, which is 144. And that equals what? Let's see, that's 265, and 49, and I've got to be careful, is 314. And I don't think there are any squares in that. 4 doesn't go into it. 9 is unlikely. So I'm pretty sure there are no squares in that. Anyhow, that's going to be the distance between these vectors, and that's approximately what? Well, 17 squared is 289, 18 squared is 324. I'd say it's about 17.7. That's my guess. You can figure it out on a calculator. Okay, but the point is, this is a very simple calculation, and another thing I'll point out is that it looks like we got all positive numbers here. Is that always going to be the case? Are we always going to get all positive numbers? Well, it's going to require a little proof. Okay, so now we're going to go on to a symbolic representation of these vectors and prove a couple of properties.